Hello students, in this class let us learn about drift velocity, relaxation time and also the expression for resistivity in terms of relaxation time. Now what we have learned from the last class, let us recapitulate what are the things we have learned from the last class. The last class we have discussed about resistance. Resistance is an opposition made by the conductor for the flow of electric charges. Next, the SI unit of resistance is ohm. Then we learned what are the factors on which resistance of a conductor depends. Resistance depends on length, area of cross section, then temperature and also on nature of the material of the conductor. And after that we have learned about resistivity. Resistivity is the resistance of a conductor of unit length and unit cross sectional area. And the SI unit of resistivity is ohm meter, and have also made a very important point that resistivity is a quantity which is a particular or which is a characteristic property of a material at a given temperature, which means it is independent on the dimensions of the conductor. Next, we have learned one more important quantity called current density. Current density is given by J is equal to I by A, that is current divided by area. The current flowing through the conductor per unit cross sectional area is known as current density. The expression for current density in terms of electric field that we have derived in the last class, that is J is equal to sigma into E, so that the direction of the current in a conductor is same as that of the electric field. This is what we have learned from the last class. Now in today's class let us learn about the drift velocity and relaxation time. Now first of all let me consider a conductor. This is a conductor having a circular cross section, and also there are many electrons on its surface. These are all free electrons. We know that when the electric field is applied to this conductor, or when we connect this to an external source like a battery or a cell, what happens is an uniform electric field will be set up here. The direction of electric field is like this, so that the electrons in the conductor will be drifted or they will be attracted towards the positive potential or against the direction of electric field. This is what we learned in the previous section. Now in the absence of electric field, that is when the electric field is not applied or we have not connected the battery, then if you consider the motion of electrons, the electrons are not having a preferred direction. They are moving randomly in a conductor. One electron may move like this, other electron may move like this, and the one can like this. Likewise, when the battery is not connected or electric field is not applied, the electrons will be having a random direction. But as soon as the electric field is applied, all the electrons are now getting a preferred direction, that is towards the positive potential. So that when the electric field is applied, all the electrons are moving towards the positive end, and the velocities of all the electrons may be different, but as the general case, if you consider for all the electrons, the average velocity of all the electrons, that will be same, and that is what we know as a drift velocity. So let us define drift velocity now. Drift velocity is the average velocity with which the electrons in a conductor are drifted towards positive potential against the electric field. Yes. This is the definition of drift velocity. The average velocity with which the electrons in a conductor are drifted towards the positive potential against the electric field. This is called as a drift velocity. I have explained you that all the electrons after applying the electric field will be moving opposite to the electric field, direction of electric field, or towards the positive potential. So the velocities, the average velocities of all the electrons is nothing but a drift velocity. This is the definition of drift velocity. Now we have to derive an expression for the drift velocity. Let us derive the expression now. For this, let me consider a metallic conductor. This metallic conductor initially having electric field equal to 0. Means we have not connected this conductor to an external source. The electric field is absent. So as I told you earlier, the electrons in the absence of electric field are not having a preferred direction. They are moving randomly. Because of the thermal excitation. The electrons in a conductor are moving in a random direction. So that if I consider as a whole, the 50% of the electrons are moving in one particular direction and the remaining 50% are moving exactly opposite to that. So when we consider the velocities, so 50% of the electrons are moving in one direction, the remaining one are moving in the other direction, opposite direction, so that their net velocity will be 0. I will call this as U. U net is equal to 0. U net is equal to 0. What does it mean? In the absence of electric field, the average velocity of free electrons is 0. So that is what you have written here. So if you write the summation of Ui is equal to 0. This is in the absence of electric field. Now consider that this conductor is now connected with a external source. Let me connect a battery now. Let us connect the battery now. Yes. Now the electrons are having a preferred direction. To move. So what happens in the case of presence of electric field? Let us see that. In the presence of electric field, I will write this like this. I will write it like this now. When an electric field is applied across the ends of a conductor. When the electric field is applied across the ends of a conductor. Now let us see what happens. I will consider a single electron now. This is an electron which is present at this end. After applying the electric field, what happens is this electron is started its motion like this. I know that there are positive ions as well as neutral metal atoms, so that this electron undergoes collision with this, but it is accelerated in this way, and it may undergo collision again, but it is accelerated in this way. It may undergo collision like this and it is accelerated like this. Even though the electrons are undergoing collisions, they have a preferred direction to move towards the positive potential. So that if I consider if A is the acceleration, of an electron, of some ith electron, acceleration can be written as force divided by mass. We know the equation from Newton's second law, F is equal to m into A. If I rearrange that equation, A is equal to F divided by m. So we have already made a statement that when a charge is placed in an external electric field, it will experience a force is equal to Q into E. But charge on an electron is taken as minus E, so that the force will be minus E into E. Now let us substitute this F is equal to minus E into E here. So A is equal to, the acceleration is written as minus E into E divided by m. So every electron in a conductor will be having this much of acceleration. Now let us consider the general case now. So I have written an acceleration by considering a single electron. Now for all these electrons, for all electrons, we know that from the equations of motion, V is equal to U plus AT. If I consider this equation for that electron, I am saying Vi, that is the final velocity of that ith electron, and this is Ui, initial velocity of the ith electron. Acceleration is same for all the electrons, and time Ti, I will write the time Ti as it is the time taken between the two collisions. Now let us make these average, the average of these things. The average of Vi, I will consider this average of Vi as this one as a drift velocity Vd, because I have already defined this. Drift velocity is the average velocity of all the electrons which are drifted towards the positive end when we connect the, or when we apply the electric field. So drift velocity is the velocity of, average velocity of all the electrons when we connect the, or when we apply the electric field. So let us write the average of this one. Average of Ui. The average of Ui is equal to 0, because I have already made that Ui is the initial velocity of electrons. See here we know that summation of Ui is equal to 0, which means when the electric field is absent, the velocity, the average velocity of all the electrons is 0. That is why this becomes 0. Average of Ui becomes 0. Now let us substitute this here, and also we have to make the average of time. The average of time, average of Ti is written as tau, which is called as a relaxation time. Now if I substitute these things here, what we will get is, instead of the average of this Vi, we can write Vd, which is called as a drift velocity, that is equal to Ui is 0, therefore I will write this as 0, plus A is known, A is already written here, A is equal to minus E into E by m. I will write that. So this is minus of E into E divided by m. Next, into the average of this Ti will be tau. So what we can write finally is, we can write the final equation. Vd is equal to, I will lay out this 0, and minus of E into E divided by m into tau. So this is the expression for the drift velocity of the free electrons in a conductor. I will write the vector equation also, because velocity is a vector. So Vd is equal to minus of E into tau by m into electric field E. So you can see the negative sign here. You can observe a negative sign in the equation. That negative sign stands for the velocity of electrons is always opposite to the electric field. See, the equation is Vd is equal to minus of E into tau by m into E, which means the velocity, the average velocity of all the electrons is always opposite to the direction of electric field. That is what the significance of that equation. So magnitude wise, the drift velocity is given by minus of E into E tau divided by m. So this is an expression for a drift velocity. This question will be asked for 3 marks in your examination. Sometimes this may ask for 5 marks also. Okay, the definition of drift velocity and also the derivation. So this is a very important question. You should be understood this one very clearly. I will explain this again. Look at the board. This is a diagram for this. In the absence of electric field, the electrons will be having a random motion. Therefore, its average velocity is equal to 0. That is what this one is. Next, when the electric field is applied to the conductor by connecting a battery or a cell, what happens is the electrons will be drifted towards the positive end. So inside the conductor, electrons will be experiencing a force due to the electric field. So that force is written as F is equal to Q into E. But the charge here is nothing but charge on electron. That is why we are writing minus of E into E. So we know that from the Newton's second law, A is equal to F by M. Acceleration is equal to force divided by mass. If I write this F as minus E into E, so we get A is equal to minus of E into E by M. So this is the acceleration of the electrons in a conductor. Now, from the equations of motion, we know that Vi is equal to Ui plus Ati. This is the equation of motion, first equation of motion. This is final velocity, this is initial velocity, this is acceleration, and this is the time. So here, this time Ti is called as the time taken between the two collisions, the time elapsed between the two collisions. So let us make the general case for all the electrons. For all the electrons, average of this Vi is written as Vd, which is called as a drift velocity. Next, the average of Ui, the initial velocity, that is before applying the electric field, that is equal to 0. We know that. So that this will be 0. Next, acceleration is known. I know the acceleration here. And then the average of time between the two successive collisions is written as tau, which is called as relaxation time. Then if I apply these things in this equation, we get this one. So 0 plus minus of E into E by M into tau. So if I rearrange the equation, we get Vd is equal to minus of E into E divided by M into tau. This is the equation for a drift velocity. If you write the vector equation will looks like this. The direction of velocity is always opposite to the electric field because we have a negative sign here. Yes. So we'll move on to the next topic now. We have to define what is relaxation time. So we know that in a conductor, when the electric field is applied across it, the electrons will be drifted in the positive direction. This is the thing we know that. So electrons, while moving, undergoes collision with some of the positive ions, also with atoms. If you consider the time taken by that electron between the two successive collisions, the time elapsed between the two successive collisions. For all the electrons, they may not be same, because the electron here can move in this path, another electron can move in another path like this, so that the time elapsed between the two successive collisions for all the electrons may not be same. So that we have to make the average time, we have to consider an average time. The equation of drift velocity also, Vd is equal to minus of E into E, tau divided by M. So we have written this tau as it is the average of time elapsed between the two successive collisions. That is why relaxation time is defined as, how to define this relaxation time? Yes, average time interval between two successive collisions of electrons when they are drifted against the electric field. This is called as a relaxation time. Average time interval between the two successive collisions of electrons when they are drifted against the electric field. This is the definition of a relaxation time. Next, we have to derive an expression for current in terms of drift velocity. Expression for current in terms of drift velocity. Yes. For this, again, consider a conductor of length L and consider a conductor of length L and area of cross section A. Right? When an electric field is applied, we know that the charges in a conductor will be drifted towards the positive end. So, we know the expression for current as delta Q by delta T. The total charges divided by the time through which they are crossing the cross-sectional area. This is what we call as the definition of electric current. Now, we can write this equation as delta Q is equal to I into delta T. I am rearranging the equation. I am writing what is delta Q. Delta Q is equal to I into delta T. I will write N is the number of electrons in a conductor. This capital N is the number of electrons or free electrons in a conductor, number of free electrons in a conductor. Suppose if you write this total charge as total number of electrons into charge on an electron. We know this from electrostatics. Electrostatics says that total charge is quantized. It can be expressed as number of electrons into charge. So delta Q is equal to N into E. So this is equal to I into delta T, and I will write this capital N as N into V, which means N is equal to, small n is equal to N divided by V from the same equation. This is a total number of electrons. This is the volume of the conductor. The total number of electrons divided by volume gives number density of electrons. This small n is known as electron number density, that is number of electrons present per unit volume, number of electrons present per unit volume. So that this N is replaced by N into V, that is number of electrons per unit volume into volume of the conductor. So this into E is equal to I into delta T. Now slightly rearrange them. I will write this V as the volume of the conductor. This is a cylindrical conductor, so that area of cross section into length gives the volume of the conductor. So that I will write this N, this V as A into L, area of cross section into length of the conductor gives volume. So this into E is equal to I into delta T. Now I will write the equation for only I. So I is equal to, I will take this delta T to the denominator, N into A into L into E divided by delta T. Take this A, right, I will write the constants inside the bracket, N into A, into E into A inside the bracket, and L divided by delta T. See, this is the length of the conductor. The length of the conductor divided by time. This length is just like a displacement of electrons. From here to here, this length is nothing but a displacement. So displacement divided by time is nothing but a velocity. You know that from the first year. So that I will write N into E into A, this L by delta T as a velocity. That velocity is nothing but a drift velocity. So we got an expression for current as I is equal to NEA into VD, where VD is a drift velocity. So that we have derived an expression for current in terms of drift velocity. So if you consider the conductor of length L and area of cross section A, let N is the number of free electrons present in a conductor. Capital N represents the number of free electrons in a conductor. So that number of free electrons divided by volume gives the electron number density, which is small n. So number of electrons present per unit volume is known as number density. Now we can write expression for current as delta Q by delta T. So if I rearrange this one, we get delta Q is equal to I into delta T. This I is written as it is, delta T as it is, but delta Q can be written as number of electrons into charge. This is from electrostatics. So but this N can be written as N into V. So N into V into E is equal to I into delta T, but I will write this V as V is nothing but a volume. So volume can be written as area of cross section into length. So that this is A into L into E, this is equal to I into delta T. Now I is equal to N into A into L into E divided by delta T. I am rearranging this equation, that's it. So NEA, if I write NEA inside the bracket and L divided by delta T, but this L is nothing but a displacement of electrons from here to here. So the displacement divided by time will give us a velocity, so that this velocity is nothing but a drift velocity. So we get I is equal to NEA into VD. So this is the expression for current in terms of drift velocity. Next we'll move on to the next topic, expression for resistivity in terms of relaxation time. This is just a mathematical derivation. We have to show that this is a mathematical derivation, so that we have to derive rho is equal to m divided by n square tau. Now let us start with an expression for current in terms of drift velocity. We know the equation. Just now we have written an equation like I is equal to NEA into VD. Here this N is nothing but number of free electrons present per unit volume. I told you that this N is a number density, electron number density. So N into E is charge on electron, A is the area of the conductor, area of cross section of the conductor, and VD is the drift velocity of free electrons. So if I write this as N into E into A, and we know that the value, we know that the equation for drift velocity, the equation for drift velocity is E into E tau divided by m. I am writing only the magnitude of drift velocity, so that we are getting E into E tau by m, because we know the equation for drift velocity, Vd is equal to E tau divided by m. I am writing only the magnitude, that is why we have substituted Vd as E into tau divided by m. Now I is equal to, so here we have E, let us multiply this with E, so this becomes E square, N into E square into E, I will write this tau first, then this is E divided by m is written as it is. I am writing like this, inside the bracket I am writing N, E into E square, and this tau, then this m, and what remains is A also. This A will be written outside the bracket. Now let us divide this A to the denominator, so that equation becomes I by A is equal to N E square into tau divided by m. N E square tau divided by m inside the bracket, and outside we have E. But we know that I by A, current divided by area, is known as current density. I by A is known as current density. So this is current density J, therefore we get NE square tau by m, this into electric field E. But we know that we have one more expression for current density. Current density is also given by this equation, J is equal to sigma into V. We have derived this in the previous section. So this is equal to equation 2. So we got two equations for J, current density. By comparing these two equations inside the bracket NE square tau by m, this is what equal to this sigma is. If I compare these two equations, J and J, E and E, so that inside the bracket is nothing but this sigma. Now let us write that. Therefore from 1 and 2 we can clearly write sigma is equal to n e square tau divided by m. But we have already know that sigma is equal to 1 by rho. Sigma is called conductivity. The reciprocal of conductivity is called as resistivity. So that rho is equal to 1 by sigma. If I write the reciprocal of this equation, we get an equation for sigma. Therefore, rho is equal to, I will write the equation for rho, which is nothing but a reciprocal of sigma. Means I have to write this in a numerator, this in a denominator. So, rho is equal to m divided by ne square into tau. So, this is the equation, this is the required equation. Rho is equal to n e square into tau. So, this is the derivation, which is also an important one, because this derivation is asked for 5 marks in your examination. It will be asked for 5 marks in your examination. So, how is the question? How they will ask the question? Assuming the expression for drift velocity, derive rho is equal to m divided by ne square tau, or simply they have given this equation. Derive rho is equal to m divided by ne square tau. So, how to derive it? First, we should consider the expression for current in terms of drift velocity. Let us start with this one. I is equal to NEA into VD. But I know that the drift velocity, the magnitude of drift velocity is given by E into E tau divided by M. Let us write this VD as E tau divided by M. Next, I will multiply this here. So, NE square into tau by M. I will write this inside a bracket and keeping A and E outside. So, A and E here. Now take this A to the denominator, that this becomes I by A. I by A is equal to NE square tau divided by M into E. Now I know that I by A, the current divided by area, is known as current density J. So that J is equal to NE square tau by M into E. Call this as equation 1. Next we know that J is equal to sigma into E. Call this as equation number 2. Let us compare equation 1 and 2. If I compare them, here we have left hand side same, and we can equate the RHS also. So E and E is same, means the quantity inside the bracket should be equal to sigma. Therefore, sigma is equal to NE square tau by M. We know that sigma is the conductivity. The reciprocal of conductivity is called as resistivity. Therefore, rho is equal to 1 by sigma. So that if I write the equation for rho, it will be m divided by NE square tau. So this is what the required equation is. Yes, up to now what we have studied is, first of all, the expression for drift velocity and definition of drift velocity, which is very important. Drift velocity is the average velocities of all the expression for drift velocity. First of all, the definition of drift velocity is the average velocity of all the electrons in a conductor which are drifted towards the positive potential against the electric field. This is the definition of drift velocity. And after that, expression for drift velocity, which is also a very important one, Vd is equal to minus of E into tau divided by M. So that equation stands for the drift velocity is always against the electric field. And after that, relaxation time, it is the average time interval between the two successive collisions of electrons when they are drifted towards the positive potential. And after that, we have derived an expression for current in terms of drift velocity. The equation says I is equal to NEA into VD. Finally, using that expression for current in terms of drift velocity, we have shown that resistivity rho is equal to m divided by NE square into tau. Yes, thank you.